Welcome back. I was still thinking about all that cool triangle stuff from the first part.
Yeah, triangles are pretty neat.
But there's got to be more to Euclidean geometry than just triangles, right?
Oh, absolutely. There's a whole world of shapes out there.
So what's next? What other shapes should we explore?
Well, now that we've got triangles down, you're ready for quadrilaterals.
What?
Quadrilaterals, it's just a fancy word for any shape with four sides.
Oh, okay. So like squares, rectangles, parallelograms.
Exactly. All those shapes you probably drew in elementary school.
Yeah, I remember those.
And they have their own special properties and rules.
Oh, really?
Yeah, which makes them super useful in geometry and everyday life.
Okay, I'm ready to level up my quadrilateral knowledge.
All right, let's do it.
Where do we start?
Well, remember how we learned that the angles inside a triangle always add up to 180 degrees?
Yeah.
Quadrilaterals have a similar rule.
Okay.
No matter the shape, the angles inside any quadrilateral will always add up to 360 degrees.
360 degrees, that's a full circle.
Right, and it makes sense because if you connect the four corners of a quadrilateral, you basically make a circle.
Oh, yeah, I see that.
It's all connected.
So cool. Okay, so let's talk about specific types of quadrilaterals.
Right.
You mentioned squares and rectangles before.
Right.
What makes them special?
Well, they're both special types of parallelograms.
Parallelogram. Okay, so remind me, what exactly is a parallelogram?
The key thing about a parallelogram is that its opposite sides are parallel.
Parallel, okay.
Think of like railroad tracks that never intersect. And because of that, opposite sides of a parallelogram are always equal in length and opposite angles are equal too.
So in a rectangle, the top and bottom sides are both parallel and equal, and the left and right sides are too.
Exactly.
And all four angles are right angles, which we know are all equal.
You got it. You're getting this.
Thanks. And a square is like a special rectangle, right?
Yeah, you could say that.
It's got all the properties of a rectangle, but all four sides are equal.
Exactly. A square is a parallelogram with four equal sides, A and D, four right angles.
So a square is like a superpowered rectangle.
Haha, yeah, I like that.
It's amazing how all these shapes connect.
It's like a family tree of shapes.
Yeah.
And Euclid gave us the tools to understand it all.
It really was brilliant.
Now think about how all this is used in the real world.
Okay.
Imagine you're building a house.
All right.
The walls need to be rectangular. The floor needs to be a rectangle. Maybe even the roof uses parallelogram shapes for stability.
So builders are using Euclidean geometry every day without even realizing it.
They are. It's all about those parallel lines and equal sides.
Wow. Euclidean geometry is like shaping the world around us.
It really is. And it goes beyond just buildings.
I like what?
Think about designing a car.
Okay.
The chassis, the doors, the windows, they all rely on the principles of quadrilaterals to make sure they're strong and stable and aerodynamic.
Wow, Euclidean geometry is everywhere. Okay, so we've done triangles and quadrilaterals now.
We've made good progress.
What other shapes are left?
Well, we can't forget about circles.
Oh yeah, circles. They're different though, right?
Yeah, they are a bit different from polygons like triangles and quadrilaterals.
Because they don't have straight sides.
Right, but they're equally important in Euclidean geometry, and they're everywhere in the real world.
All right, I'm ready to go full circle. What do we need to know about these curvy shapes?
Well, one of the most basic concepts is circumference.
Circumference.
It's the distance around the circle, like the perimeter of a circle.
Okay, I remember that.
And to calculate circumference, we use a special number you might remember from school pi.
Pi. The never-ending decimal.
That's the one.
I remember memorizing all those digits after the decimal point.
Yeah, a lot of people do.
But I never really understood what it meant.
Well, pi is a pretty amazing number. It represents the ratio of a circle's circumference to its diameter, no matter how big or small the circle is.
Oh, wow.
It's a constant value, about 3.14, but the decimal goes on forever without repeating.
So pi is like a secret code in every circle in the universe.
Uh-huh, you could say that.
That's mind-blowing. But how do we actually use pi to calculate a circle's circumference?
The formula is pretty simple. It's circumference equals 2 times pi times the radius of the circle.
Okay.
The radius is the distance from the center of the circle to the edge.
Right. So if I know the radius, I can just plug it into that formula and boom, I know the distance around the circle.
Exactly. You got it.
I'm starting to feel like a geometry whiz.
Uh-huh. You're doing great.
So we can figure out the circumference.
Yes.
And then what about the area of a circle?
You're right. The area is the amount of space inside the circle.
And that formula uses pi too, right?
It does. The area of a circle is equal to pi times the radius squared.
Pi is everywhere. It's like the king of circle calculations.
Yeah, it's pretty important.
So these formulas are useful for things in real life, right?
Oh, absolutely. Imagine you're designing a circular garden. You'd need these formulas to figure out how much fencing you need for the perimeter, and how much soil to fill it.
Makes sense. I'm seeing circles in a whole new light now. It's not just about pretty shapes anymore.
Right. It's about understanding their properties and using them to solve real problems.
Exactly. And we haven't even talked about some of the more complex circle stuff like tangents and chords and arcs.
We haven't. There's always more to learn.
My brain is already full of geometry. Maybe we should take a break and come back for the last part of our deep dive.
That sounds like a good plan.
We can explore those more complex ideas and see how everything we've learned about Euclidean geometry all comes together.
I'm looking forward to it.
All right, we're back for the final part of our Euclidean geometry deep dive.
Yeah, it's been quite a journey.
We've come a long way from Euclid's postulates to triangles, quadrilaterals, circles.
We've covered a lot of ground.
I'm excited to see how it all fits together and how this ancient knowledge is still relevant today.
It really is amazing how these simple concepts have had such a huge impact on human civilization.
You're right. We've talked about some real-world applications, but I want to go deeper.
Okay.
What are some specific examples of how Euclidean geometry is being used in, cutting-edge fields today?
Well, let's take computer graphics, for example.
Okay.
When you see those crazy realistic 3D models in video games or animated movies,
Right.
it's Euclidean geometry that makes it all possible. It provides the framework for creating those virtual worlds.
Oh, wow.
Every object, every surface, every movement, it's all based on the principles of points, lines, angles, and shapes.
So even in the digital world, we're still using the geometry of the real world.
Exactly. It's all connected.
That's so cool. What about something like medical imaging? I never thought geometry would be involved in that.
It's actually crucial. Techniques like CT scans and MRI use super complicated algorithms to create 3D images of the inside of our bodies.
Wow.
And guess what? Those algorithms rely heavily on Euclidean geometry to rebuild those images from the data.
So it's like Euclidean geometry is helping doctors see inside us.
It is, just like architects use it to design buildings and engineers use it to build bridges.
That's incredible. Are there any other surprising places where it pops up?
Believe it or not, Euclidean geometry even plays a role in astronomy.
Astronomy. Really?
Yeah, when astronomers are trying to figure out the distances to stars and galaxies, they use a technique called parallax.
Parallax, what's that?
It's based on triangulation, basically using triangles in space to measure the universe.
Wait, so you're using triangles to measure the universe?
Exactly. By looking at a star from different spots in Earth's orbit, astronomers can measure the tiny shift in the star's position.
Okay.
And using those measurements and some trigonometry, they can calculate the distance to that star.
It's amazing that we can measure such huge distances using the same principles we use to build houses and design cars.
It's all thanks to the fundamental nature of Euclidean geometry. It's a system that describes the relationships between points, lines, and shapes in a way that's always true, whether we're talking about tiny things or huge things.
Euclid was a genius. He gave us a way to understand the universe that's lasted for centuries.
He really did.
But now I'm kind of curious about those other types of geometry. We talked about the non-Euclidean ones.
Yeah, those are pretty interesting.
If lines can curve in those systems, does that mean everything we've learned about Euclidean geometry is wrong?
That's a great question. And it's one that mathematicians have been debating for a long time.
Oh, wow.
Non-Euclidean geometries challenge our basic ideas about space and shape, but that doesn't mean Euclidean geometry is useless.
Right.
It's still really useful for describing the world as we see it.
So it's like using different tools for different jobs.
Exactly. Euclidean geometry for everyday stuff and non-Euclidean geometries for exploring more extreme things like black holes or the fabric of space-time.
That makes sense.
Yeah.
And even though they seem like totally different systems, I bet there are some connections between them.
Oh, there definitely are. Exploring those connections is a whole other deep dive, maybe for another time.
I'm adding it to the list.
Yeah.
But I think we've covered so much in our exploration of Euclidean geometry.
We have. It's been a great discussion.
Any final thoughts before we wrap things up?
I just encourage everyone to look for the principles of Euclidean geometry in the world around you. You'll be surprised how often you see those shapes, those angles, those relationships, in everything from nature to the things we build.
Great advice. And remember, even if you don't always realize it, Euclidean geometry is shaping our lives in so many ways.
It really is.
Thanks for joining us on this incredible deep dive into the world of Euclid.
It was my pleasure.